Welcome back, class. So this is the last lecture of electrochemistry, third lecture number 9. And in this lecture we will discuss about some thermodynamic quantities, the thermodynamic quantities of cell reaction. Thermodynamic quantities of cell reaction. Thermodynamic quantities, that means the Gibbs free energy, the enthalpy, entropy. So first, let's understand that what is the need here of this thermodynamics quantity. Well, the Gibbs equation, the Gibbs Helmholtz equation G equals to H minus Ts. Okay, and if you go in detail of this equation, uh, there is another form of this equation which is the most common form actually, and that is the del G equals to del H plus T del G upon del T at constant pressure. This is another form of Gibbs equation, Gibbs Helmholtz equation. Okay, so what is the role of here, what is the role of this equation here? When we go for the application of this equation, the application part of this equation, there is an important application of this equation. If any redox reaction, like if we take zinc plus copper sulfate, then this will give zinc sulfate and copper. Any redox reaction is allowed to take place in a beaker. Okay, so what will happen? Heat will evolve. Here what will happen? Heat will evolve. When this reaction is allowed to take place in a beaker, what will happen? Heat is evolved. Earlier it was believed that if the same reaction is allowed to take place in an electrochemical cell, the electrical energy produced is equivalent to the heat produced. Okay, we all know that if this reaction is take place, heat is evolved. Okay, but if the same reaction is allowed to take place in a electrochemical cell, the electrical energy produced is equivalent to the heat evolved. Although later uh, there are several cases which shows that the electrical energy produced is not equivalent to heat allowed. Okay, earlier it was believed that the heat electrical energy produced is equal to heat evolved. Okay, but later it is revealed that it was revealed that the electrical energy produced is not equivalent to heat allowed evolved. Okay, so finally the Gibbs Helmholtz stated that the electrical energy produced, this is the statement very important, the electrical energy produced was equal to decrease in free energy. This is very important. Decrease in free energy. Okay, and that is why we need to discuss the thermodynamic quantities of cell reaction. Again I'm repeating, this if this reaction takes place in a closed beaker, what will happen? Heat will evolve, okay. But if the same reaction is going to take place in a electrochemical cell, electrical energy will be produced, and this electrical energy is equal to the heat evolved. This was the earlier statement, but there are several contradictory statements also there, that the heat evolved is not equivalent to the electrical energy. Finally the Gibbs Helmholtz stated that the electrical energy produced is equal to the decrease in the free energy. So we know that the electrical energy produce is NFE. N is the number of electron, F is the Faradaw constant, okay, and E is the EMF. So decrease in free energy is what? Decrease in free energy. Decrease in free energy means minus del G. Minus del G equals to NFE. Okay, so this is an important one. Got it? And one more thing you should keep in mind, that this is another form of Nernst heat theorem. Nernst heat theorem. This we had already discussed in the thermodynamics chapter, second unit in your syllabus. This we had already discussed over there. But I'm correlating these things to electrochemistry. What is the need to discuss it again here? Okay. So this is what the relationship. Now by putting value of this into this equation, what will happen here? If we put del G value in this equation, the equation will look like this: minus NF E del H plus T del, here minus NF E upon del T at constant pressure. Okay, then just divided by minus sign, divided by minus. So here this NFE will be positive, del H will be negative, T, this minus will be escape out, so del NFE upon del T at constant pressure. Okay, then again you can divided by NF. So once you divide it NF, the equation looks like E equals to minus del H upon NF plus T d del E upon del T at constant pressure. So this is the value of equation for the calculation of EMF. Okay, this is how you can calculate the EMF. Now let's derive the other equation also. What are the other equations? So if you want to find out the value of enthalpy, so from here you can calculate the value of enthalpy also. You can take this equation in order to calculate the value of enthalpy. So let's take this equation here, this equation. Okay, so here what will happen if we want to find out the value of del H? So del H equals to what? Del H will come to this side. Okay, So del H equals to T, then d NFE upon del T, and this NFE is come to this side, that means NFE. Okay, then here is T, okay, del H equals to, then if go for the, so this is how you can find out. You can go further calculation also. Then del G equals to del H T del S. We all know that. If you want to find out the value of del G, we already calculated. Del G is equal to NFE. For this del H, from this equation, you can also divide by del NF, so you'll get further simpler calculation also. Okay, if you divide this by NF, what will happen here? NF T del E upon del T minus E. Okay, I can write it here. Divided by NF, what you will get? Del H equals to uh, del H equals to NF, and here it is multiply, no? T del E upon del T minus E. Now for del S, T del S, you can write is T del S equals to what? Del H minus del G, or del S equals to what? Del H minus del G upon T. We have a value of del H also, we have value of del G also. So for del H value, we can write N F, then T del E upon del T P E, and for this we can write NF E. This is the value of minus, so this will be in plus divided by T. If you calculate all this, if you multiply, divide, subtraction, so del S equals to what? NF del E upon del T at constant pressure. So this is another, so this is how you can calculate the del G, del H, del S. Okay, then we have one more, and that is the equilibrium constant. So let's discuss that, how that equilibrium constant will be calculated. So for the equilibrium constant, as we know that the equation is the equation for the equilibrium constant is we can write Zn plus Cu plus 2, so this will give you Zn plus 2 and copper. Okay, so what is the value of K here? I'm talking about the equilibrium constant. Okay, equilibrium constant K, so value of K is Zn plus 2, then copper, then copper plus 2 and Zn. So this solid will constant, so K equals to Zn plus 2 and copper plus 2. Okay, the E equation, the E cell equation is what? E cell equals to E naught cell minus RT upon 2F. For this equation we have 2 electron. Okay, and L N Zn plus 2 and Cu plus 2. So this is what? This is K. So E cell, E naught cell, RT upon 2F and ln K. At equilibrium, E cell is 0, which we had already discussed. Reversible cell, irreversible cell, and at equilibrium. So at equilibrium, E cell value will be 0. This value will be 0. So this E naught cell equals to what? RT upon 2F ln K. And if you go for the further calculation, this is 2.303 RT upon, this is NF, NF, the simpler one, okay, log K, or E naught cell equals to 0.059 n log K. So here you can calculate the value of K, the equilibrium constant, okay, like this is E naught cell into n upon 0.059 log K. So this is how you can calculate the equilibrium constant value. So these are some thermodynamic quantities which we have to discuss. Uh, Here we have discussed the value of del H, then del G, then del S. This is very important. Many questions are asked on the basis of this equation. So you have to take care of this equation, okay, because this is very important one. And I'm just giving you one numerical, so this will help you to find out, and this numerical is based on the Gibbs Helmholtz equation, okay. So numerical is question: the free energy change involved in a process is minus 1235 joule at 300 Kelvin and minus 1200 joule at 300 Kelvin. So this is the value of free energy, okay, del G. And calculate the change in enthalpy of the process. Calculate del H for the process at 305 Kelvin. So this is the question for you. The free energy change involved in a process is minus 1235 joule at 300 Kelvin and minus 1200 joule at 310 Kelvin. Calculate del H for the process at 305 Kelvin. So just write your answer in the comment box or WhatsApp to my WhatsApp number, and if you have any doubt you can ask. Thank you so much.